Hi guys, so today's video is going to look at polynomial graphs. So this is what we did the first day that I was here with you guys. And what this is basically talking about is how to draw graphs of these polynomial functions, and we're going to do this without using a calculator. So the first thing that we looked at was how to find the degree of a polynomial. So the degree of a polynomial can be very simple. It's simply the highest exponent. So if you have a polynomial written out in its standard form like this one, it's just your biggest exponent. So that first one would be the fifth degree. The second one, it's out of order, so we need to make sure we actually find it, and that would be a fourth degree polynomial. Now, if you see something like number 3, where it's written out in intercept form as your factors, we would need to consider, if this were FOILed out, what would be the highest exponent of x? Well, I would have x squared, and then x to the first, times x to the first. So if I did x squared times x, that would give me x to the fourth. So this would be a fourth degree polynomial. So if you see your polynomial written as intercepts, you need to make sure you remember and add up basically those multiplicities. All right, now let's look at end behavior. End behavior is determined by two things. We look at the leading coefficient to figure out if it's positive or negative, and then we look to see if the degree is an odd or even number. Now this is not the same as the function being odd or even. We'll look at that here in a second, but it is telling us if the degree is an odd or even number matters. Now, instead of memorizing this chart, the best thing you can do is think about basic parent functions that you already know the shape of. So the first case we're going to look at is if we have a positive leading coefficient and an odd degree. So a positive leading coefficient with an odd degree, that's like y equals x. The ends of y equals x look like this. So that's what my end behavior would look like for any polynomial with an odd degree and a positive leading coefficient, such as example 1 up here. Okay, that's what my end behavior would look like for this graph. Now, again, you guys learned earlier this year how to write end behavior. Okay, so as x approaches positive infinity, what is my f of x doing? In this case, it's approaching positive infinity. As x approaches negative infinity, my y is approaching negative infinity. Now let's think if this was an odd degree and a negative leading coefficient, that's going to look like y equals negative x, which looks like this. Now what happens in the middle of this graph we'll talk about here in a second, but for now we're just looking at the ends. Okay, in this case, as x approaches infinity, f of x approaches infinity. As x approaches negative, oops, I'm so sorry guys. As x approaches infinity, y is approaching negative infinity. Again, as my x's are getting bigger, my y's are getting smaller and smaller. As x approaches negative infinity, y is approaching positive infinity. So if it's not an odd degree, it could be an even degree. So the easiest way to figure this out is to, again, think of a basic parent function that you know that has an even degree and a positive leading coefficient. The easiest one's y equals x squared. We all know what y equals x squared looks like. My ends are going up. So as x approaches infinity, y is approaching infinity, and as x approaches negative infinity, y is also approaching negative infinity. So even degrees are going to go in the same direction. Now let's look at y equals negative x squared. Okay, that's negative leading coefficient and an even degree. Both ends would be going down. So both of these are approaching negative infinity. So let's look at two examples here. Again, to determine the end behavior, we need to consider the degree and the leading coefficient. This one would be a fifth degree and a negative leading coefficient. So if it's a negative leading coefficient, an odd degree, my ends would look like y equals negative x, but we're going to write that end behavior the correct way. So we would say, as x approaches infinity, y is approaching negative infinity. As x is approaching negative infinity, y is approaching positive infinity. And let's look at our second one. This one, to find the degree a little bit harder, we need to consider if this were multiplied out, what would it be? So this is x to the first, this is x to the first, that's x to the second. So this would be a fourth degree, which means it is a positive leading coefficient because there's no negatives out in front or in front of any of our x's. So that is an even degree. So positive leading coefficient and even degree, both ends are going up. That's a really bad arrow, but you see what's happening. So what that means for us is as x approaches infinity and as x approaches negative infinity, my y's are approaching infinity. So now that we know what the ends are doing, we need to figure out what the middle of our graph is doing. Now that is dependent on our x-intercepts and the multiplicity of the x-intercepts. So multiplicity is probably a new word for you guys. All that means is the exponent of the factor. Okay, it's the exponent of the factor. It's how many times the factor repeats itself. So for example, if your polynomial had x minus 2 times x minus 2, that factor is there twice. The multiplicity is 2. We could write that as x minus 2 squared. So it's the exponent of the factor. All right. If the multiplicity is an odd number, the graph will cross the x-axis at that point. Okay. Now, the bigger an odd number it is, the flatter it gets as it approaches. So think about the difference between y equals x and y equals x cubed. Okay. They both still cross through, but you notice how x cubed, it gets flatter as it approaches that 0, whereas y equals x, it just goes straight through. Now, if it's an even number, then your graph will be tangent at that point. Sometimes we say touch, okay? It bounces back. So think about what y equals x squared looks like. Okay, y equals x squared, at that point, it's tangent at 0, and it bounces back in the same direction. So we're going to use this information to find what our graph does at these points. So here's an example that's in intercept form already. So my zeros would be 0, -4, and 3. Now what my graph is going to do with those points is dependent on the exponent of that specific factor. So x is raised to the first power. 1 is an odd number, so at 0, your graph will cross. X plus 4, that factor is raised to the first power. So at -4, your graph will cross. Now 3, x minus 3 is raised to the second power. Because the exponent of that factor is 2, your graph would be tangent at that point. So I'm going to sketch real quick what this graph would look like. All right, so in behavior, first of all, overall this is a 4th degree, which is an even number, and a positive leading coefficient. So my ends are both going to be going up. All right, we know that this graph is going to have an intercept at -4, at 0, and at 3. And then we know exactly what our graph is going to do with those points. At -4, my graph is going to cross. All right, at 0, my graph is going to cross. But at 3, my graph is going to be tangent, which means it touches that point and goes back. And if you look, your end behavior matches. So if you've done this correctly, your end behavior and your zeros will match. All right, now down below, that's just some examples of what polynomial functions look like. Again, it says it will be nice, smooth curves. Okay, there's no sharp turns or holes in a polynomial. Where the graph changes direction from increasing to decreasing, okay, or from decreasing to increasing, those are your turning points. All right. Specifically, we can classify them as one of two things. The most number of turning points it could possibly have is n minus 1. So if you look at these two graphs here, this graph has 2 turning points. Now this point right here, a lot of times people want to say it's a turning point. It is not, okay? It does not change from increasing to decreasing at that point. So this only has 2 turning points. The graph next to it has 3. Now specifically, we can classify those turning points as either a local max or min or a global max or min. The word in parentheses is interchangeable, so you may see local or you may see relative. They mean the same thing. Global and absolute, those mean the same thing. Now a local max or min is basically a turning point with a high or low point relative to the points around it. So for example, this point right here, that is a local minimum. And it's a local minimum and not a global minimum because it's not the lowest point on the entire graph, but it is the lowest point relative to the points around it. Very similar, this point right here is a local maximum. It's not the highest point in the graph, but it's the highest point relative to the points around it. All right, and then let's look at this graph next to it. This also has another local max, but even more specifically, this graph has a global minimum, because this point here and this point here, which has the same y value, that is the global minimum of the graph. Now let's say instead this graph looked something like this. Okay, this point would be our global min, and then that point would be a local min. So it is possible to have both on your same graph. All right, so let's look at a couple of examples. Okay, so we're going to go ahead and try to find all this information about this, and we're also going to graph them. So this graph is third degree because it is x squared times x to the first. This graph has x-intercepts, or zeros, that's the other word for it, at 0 and at 2. 0 comes from this factor, 2 comes from that factor. At those points, at 0, that graph is tangent. We know that because the exponent of that factor is an even number. At 2, your graph is going to cross the x-axis because the exponent of that factor is an odd number. Now I'm going to go ahead and sketch just a rough sketch of what this is going to look like. Now without a calculator, you can't get very specific about how high or low these maxes or mins will be, and that's okay. But we're going to just do a rough sketch here. So end behavior is going to look something like this. I've got a 0 here and a 0 here. I'm going to be tangent at 0, and I'm going to cross through 2. So what I can see here, this graph has one local min and one local max. And I said the wrong thing at the very time, but this is a local max and this is a local min. So without a calculator, we can't find what that value is, but we can at least get a rough sketch to see kind of where they occur. And this graph has 2 turning points. Remember, it can't have more than 1 less than a degree for turning points. So this graph couldn't have 6 turning points. It could have less than 2, but it cannot have more than 2. All right, let's try example 2 here. This is also third degree because all of these are to the first power. My intercepts are 0, 2, and -2, and it is going to cross at all 3 of those places. Now I'm going to do a rough sketch here. End behavior is the same. 0, 2, and -2. I'm going to cross, cross, and cross. So because I have to cross through all those points, that gives me a local max and a local min. So I have one of each, and I probably should have specifically said right there those were local. And this graph has 2 turning points. All right, so if you feel pretty comfortable with this, I would pause the video and I would try these 2 examples on your own and see if you can get them. All right, so example 3, that is going to be a 4th degree polynomial because I have 3 plus 1. My zeros will be 0 and 2. It will cross through both of those places. Specifically though, at 0, it's going to be a little bit flatter as it crosses through. Again, think about what y equals x cubed looks like, but it's going to cross through both of them. So in this one, I'm going to draw kind of a rough sketch, but I also want to show you what the actual graph looks like so you can see it just a little clearer. All right, end behavior, we know that this is going to be positive and even, so both ends are going up. All right, sorry guys, we got cut off by the bell. So I know we had already done our degree and our x-intercepts. We said they were both cross. However, at 0, it was going to cross more. We said our degree was 4 and positive leading coefficient. So my ends would look like this. So at 2, I have a 0. At 0, I have a 0. So this is going to curve, and let me widen this a little bit so it's a little easier to see what's happening here. So here's 1, here's 2. There's my ends. Oh man, I am struggling drawing, guys. So instead, let me just show you what the actual graph here looks like. Basically, your curve here is going to look more like y equals x cubed, but your teacher is not a very good drawer. That's why whenever you guys have to draw these without a calculator, we're just looking for a rough sketch. We're looking for what's happening with our ends, what's happening at our zeros approximately here. If you need another point, you can also use your y-intercept, but in this case, our y-intercept is just 0. So let me show you the actual graph. It's the one on the left here. Okay, so this is what my graph would look like. And you can see right there at 0, your graph is flattening more as it gets to that point, and then just straight crossing through 2. You'll also notice this graph only has one turning point, and it is a global minimum. Okay, this graph has no maximums on it. This is not a turning point, that is not a min, that is not a max, because your graph does not change from increasing to decreasing. Your graph continues to decrease through the entire thing. Now let's go back. We just talked about our local mins and maxes. Let's look at example 4. Example 4 should be a 4th degree with 4 different intercepts. All of those are cross intercepts. All right, and again, I can do a rough sketch here. We're going to cross through 4 different points. So cross, cross, and cross. Positive leading coefficient, cross, 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 cross. And now on this one too, because we don't know exactly what these values are without a calculator or calculus, which you have not learned yet, I'm going to show you guys again what the graph here looks like. Now again, you should be able to do a rough sketch of this graph on your own. But mins and maxes, we know at least there's 3 turning points. But to see again exactly where these points fall, I know would be hard without a calculator. So this graph has a local min here, a local max here, and a global min down here. All right, so then the last thing not quite the last thing, but almost the last thing. Just reviewing some of our terminology about increasing, decreasing, and positive and negative intervals. But we're going to work backwards, which is a little bit harder. Okay, so this tells us, sorry about that. So this tells us where our graph is increasing and decreasing and where it's positive and negative. I think these kind of problems, it's easier to work with this information first because that information tells us where our x-intercepts are. Because the only place your graph can change from positive to negative is at an x-intercept, which means at -2, your graph changes from positive to negative. At 3, your graph changes, and at 5, your graph changes. Sorry guys, lots of interruptions today. So -2, 3, and 5 are all x-intercepts because that's where our graph changes from positive to negative. So what I'm going to do now is I'm going to shade where our graph is positive and negative. So this graph, it tells me, is greater than, it's greater than 0 from -2 to 3. So in between -2 and 3, my graph is positive. In between 5 and infinity, my graph is positive. In between -infinity and -2, my graph is negative. And from 3 to 5, my graph is negative. So somewhere in those ranges, I will have a graph. The last thing I need to consider is where this graph is actually going to turn to go through these points. That's where this top information comes in. So if my graph was increasing until 0 and then it changes to decreasing, that means when x equals 0, I have a turning point. At x equals 4, my graph switches again. So that's going to be another turning point. So at x equals 0, I'm going to plot my turning point. How high it is doesn't matter. It can still meet all this criteria, but it has to be somewhere in the positive range because I know my graph is greater than 0 in that interval. At 4, I know it has to be negative somewhere because, again, that graph is below my axis at that point. So at this point, I'm just going to connect my dots. Again, there are multiple correct answers, so the height of those curves can be anything, but it's important to know where they are. All right, the last thing we're going to look at very briefly is just an even and odd function. And the reason I really want to look at this now is just because it's easy to get this mixed up with an even and odd degreed function. So just because a degree of a polynomial is odd or even doesn't mean the function is necessarily odd or even. Odd and even functions are very specific. A function is even. Algebraically, if I plug in negative x, if I get the exact same function. The graph is going to have y-axis symmetry. All right, a function is odd if I plug in negative x and I get the exact same function, but all the signs are backwards. And that graph is going to have origin symmetry. Two easy examples. Y equals x squared is even. If you think about the graph, it's the same on opposite sides of the y-axis. Y equals x has origin symmetry. That graph, if I were to take the part in this quadrant and fold it back over across y equals 0, it would be the exact same. So let's try these examples. So I'm going to replace x with negative x. If I do negative x to the third power, it is going to be a negative x to the third power, because it's a negative times a negative times a negative. If I do negative 7 times negative x, that's going to give me a positive 7. Well, this function is the exact same as my original, but all of my signs are different, which means it's the same thing as the original function with a negative on the outside, which means that this function is odd. All right, if we look at the second one, I'm going to replace x with negative x. That gives me a now positive x to the fourth, because if I do a negative times a negative times a negative times a negative, it is a positive. A negative times a negative is a positive, which means I have the exact same as my original function. If it's the exact same, it is even. But a function does not necessarily have to be odd or even. So let's look at this last one. If I replace x with negative x, a negative times negative times negative is negative. But this is not the exact same as the original, and it's not every single sign different. Because if I factor out that negative, the inside is not the same as the original. So this function is actually neither even nor odd. So even though the degree is odd, we can still use that information to find my end behavior. But that function itself is not necessarily odd. And that's just a very specific type of function. But we'll look at that more later on this year. So that is it for graphs. Again, the biggest things to know, end behavior, your zeros, and your multiplicities, what that's going to do to your zeros. And knowing that information can give you a pretty good sketch of your graph.